I have today afternoon the great pleasure to introduce Olga Mesa. She's also my friend, and she's an architectural designer, researcher, and educator. She's an associate professor at architecture of Roger Williams University and co-director of this program. Her research was published, and still she's publishing in internationally journals, and she's also co-director of Nuova Studio. And her firm has projects in the United States, Colombia, Honduras, and Mexico. She has worked as a number of years as a research associate at the Harvard University at Material Process and System Groups and continues to collaborate with its members. Olga earned her master's degree, Master of Design Studies at Harvard Graduate School of Design with the technology concentration, and she got a prestigious Daniel Schodek Award for Technology and Sustainability. She received her Bachelor of Architecture from Rhode Island School of Design and was awarded as a Henry Adams Gold Medal for Design Excellence. Now I'm really curious to hear what you can tell us. Please.
Thank you, Milena. Thank you for that presentation. Hello, everyone. I'm Olga Mesa, and thank you for inviting me to be here. And thank you all for attending my talk titled Choreographed Matter. I will share a few projects where I hope my research and approach to design is evident, which is mainly to integrate both the functional and the expressive performance of a given work. My collaborator, Nathan Fash, and I have called this approach Performance Square. So Milena already went through this introduction. I just wanted to add that I'm a director of Nuova Studio, and the mission of our nonprofit firm is to leverage research, architectural design, construction, and material innovation to enhance education, the environment, culture, and communities. And that I will share some projects that have been done while being a research associate at the Harvard MAPS group. I strive to make my research, teaching, and practice align, nurtured, and advance one another. For this talk, then I chose projects of different scales and context, and I will make connections between the work of our nonprofit, my research on material systems, and teaching. The first project is an investigation entitled Woven Compliant Composites. This research is meant to contribute to the design of kinetic architectural components and was done in collaboration with Martin Bechtold, Saurabh Matre, and the help of others. Kinetic elements emerge from the need to adjust to changing environmental or programmatic conditions. However, moving elements in buildings remain a specialty application requiring complex mechanisms. Harnessing the inherent flexibility of materials, compliant mechanisms offer new opportunities for the design of kinetic systems in design and architecture. These elements are typically made with polymers, but have long been realized in the vela systems of, let's say, ancient Rome, and also in the sails of boats. And although tensile membrane designs have been applied in architecture, the kinetic application featuring membranes are rare, and also even rarer the ones that use fabrics for kinetic designs, even as developments of technical textiles have significantly improved and expanded. So we saw an opportunity in using woven systems for kinetic architectural components to expand existing work on compliant surface systems. Our goals were as follows: that shape, change, and actuation methods should allow for any combination of environmentally driven, passive, and user-determined active transformation. Designs should allow multiple elements to be actuated with few and simple actuators. It is desirable to achieve doubly curved forms in order to produce stiff three-dimensional configurations, and that fabrication methods should be simple, with emphasis on producing flat composite forms in non-actuated stages that minimize cost, the mold costs, which in the composite industry are quite pricey. So in terms of the relationship between geometry and material behavior, our research uses composites to design kinetic compliant mechanisms that behave as a hybrid between a fabric and a surface. Undergoing shear buckling, reversible three-dimensional configurations are achieved by using the bias of woven fabric. So in our work titled Woven Compliant Composites, the system achieves nonlinear response of compliant materials through buckling. We sought to minimize the use of complicated motorized mechanisms to obtain a kinetic response that would allow building skins components to open and close to temporarily produce a porous skin. As some of you might know, woven fabrics are anisotropic materials with different elastic constants based on the direction of the applied tensile force. So Poisson ratio and Young's modulus for a fabric are highest where the direction of tensile force is at 45 degrees relative to the weave direction. So our design utilizes the material and geometric principles, these material principles basically. So the system uses a combination of high Poisson ratio and the small but significant in-plane surface stiffness of composite fabrics. The fabrication method allows flat composites to transform into doubly curved kinetic elements without the need for molds, which, as I said, were pretty expensive to fabricate in the composite industry. The relationship between the fabric type, weave, matrix laminations, and localized reinforcement was studied to achieve repeatable and durable functional components that display instant transformations through the production of several samples. In the context of our research, when the intended behavior was defined as the deformation necessary where two opposite corners perpendicular to the axis of actuation would touch. So following the geometrical analysis of woven composite fabrics, a series of samples were produced to fabricate durable composites that allowed controllable and repeatable transformations from flat to doubly curved surfaces. Each sample was tested to determine behavior type, sample durability, actuation force, displacement of corners, and transition stages. Our results indicate that the intended behavior was achieved by either using a stiffer woven fabric or by adding central fiber reinforcement perpendicular to the axis of actuation. In this slide, samples 2 and 3 are showing the desired behavior, whereas 1 is deforming in that configuration by its own weight. All were infused in a silicon-based matrix. In terms of finite element analysis simulations, since our fabrics consist of perpendicularly oriented fibers immersed in a soft matrix, two computational models were used, the Neo-Hooken and the Holz-Apfel model. Although Neo-Hooken models are used to predict nonlinear strain behaviors, the Holz-Apfel model approximated the behavior of the physical samples better as it takes into account the anisotropic behavior of fabrics. Given the closed arrange agreement to physical test, this model was used to simulate the compliant composite mechanisms in single modules. And here's a prototype of the tessellated patterns with cuts that allow the woven form to emerge when pulling force is applied, but now as a whole surface. Architectural applications were proposed using compliant composites as kinetic surfaces for facades or interior partitions. Here, tessellations were generated by patterning a single monolithic composite fabric to achieve varying degrees of porosity and change in three-dimensional shape. The adjustable surfaces were actuated efficiently by reducing the number of actuators per module and instead actuating uniaxially or biaxially on an array, producing different degrees of porosities. These were reversible in a matter of seconds once the force was not applied. So you see here the variable porosities based on the axes, and the picture on the left it shows the prototype being pulled along the x-axis, in the middle being pulled along the y-axis, and the one on the right shows actuation on both axes, displaying the highest porosity. We believe that this material system has great potential in creating skins that can provide solar control, regular view and light, and in doing so with a quality of movement that holds great promise for expression and that they are quite light. Oops. In conclusion, kinetic response is generated without the use of complicated mechanisms by relying on material properties and its relation to geometric principles. This work attempts to expand the work on kinetic surfaces with the advantage of ease of actuation and fabrication. This moldless technique proposes an alternative for the composite industry and expands research on adjustable skins, such as differential swelling of thin wood elements and buckling of composites, by proposing a simple actuation method based on the mechanics of fabrics. These surfaces can be used in architectural applications, such as facades, shading mechanisms, and interior partitions, where functional and performative qualities are desirable. This next project, titled Entretejidos, Espacios de Chuspata, aims to expand the work of compliant woven structures using composite biomaterials at a larger scale. For this, my collaborator Nathan Fash and I used an aquatic reed called Chuspata that grows in the Pátzcuaro Lake in Mexico. We designed and conducted a week-long workshop in collaboration with weavers from Iguazio, along with architecture participants. We developed a pavilion in Pátzcuaro to illustrate how this bio-based material can perform an architectural role in numerous ways, while supporting the local habitat, economy, cultural heritage, and identity. Our research asked or tried to answer if we could deploy this Chuspata reed at an architectural scale, because mainly is deployed just at the scale of the object in this region. And use it to provide shading and space making while still harnessing the environmentally favorable properties of this as a raw material, and also its cultural significance through the tradition of weaving of the area. As part of the workshop, where collaborating artisans shared with us in a very generous way how to handle the material, from harvesting to weaving, and taking particular care of its moisture content at the various stages of the process. We observed that these practices and the main traditional patterns are possible due to the morphology of the stock, including its variable section, pliability, and compressibility. Using drawing and material tests that hybridized weave patterns, we explored how the morphological characteristics of the reed could be harnessed, along with the geometric characteristics of the common weave patterns to achieve porosity, shading, rigidity, visual appeal, and three-dimensionality in architectural components. The most promising prototypes were selected to be further developed into either horizontal or vertical architectural surfaces. We're still in the process of applying the kinetic performance to these structures seen in the previous project, and working on tests to enhance the durability of these materials with natural coatings, since the workshop was only a week. But the pavilion that we constructed offered new considerations at the human scale, such as making connections between the small-scale details of the weave and the overall graphic presence of the woven skin at the distance. So when we consider the environmental benefits of the bio-based material in and on itself, the advantages of working with a non-toxic material that is very pleasant to work with, the cultural resonance embodied through the artisan weaving tradition, and the reduction possibly of cooling energy demand provided by solar shading, we can see the numerous forms of qualitative and quantitative performance that are at play, illustrating the concept that I'm interested, the one that I previously talked about, performance square. The next project is crease synchronized gate through folded geometry, a very different scale. I'm going to share this because it still uses geometric and material principles to achieve minimal actuation for an ambulatory small robot with complex gait. This is the result of an investigation with Malika Singh and Sarah Matre, and the advice from Chuck Huberman. So with the vast example of ambulatory robots that have expanded in the last decades, traditional legged robots need engineering expertise and the use of specialized fabrication technologies. Microelectronic mechanical robots are useful for a wide variety of applications, yet in most cases they're difficult to fabricate and excessively intricate. Advances in pop-up laminate constructions have generated a modal shift in the development of robot morphologies due to their ease of fabrication and scalability from the millimeter to the centimeter scale. This research continues to investigate the link between kinematics and pop-up origamic structures in robotics. The objective was to design a robot that exhibited compelling gait and efficient and controllable locomotion while minimizing the number of motors. Chris, an origami robot that emerges from two-dimensional sheet into three-dimensional configuration, was developed. So by amplifying the simple rotational motion through the geometry of folds of the robot, a complex gait was achieved with the minimal motorized actuation of one or two motors, depending on the variation. Differences in gait, control, and steering were studied through physical and computational models. Untethered creases that sense their environment and steer accordingly were developed. The range of movement in relation to the geometric pattern of folds was studied using, was studied physically and digitally, applying principles of parallel spherical linkages to folded geometry. In its three-dimensional configuration, Chris has 4 symmetrical legs joined by a modified 8-fold water bomb base, where one of the folds was omitted to produce a stable ground while enabling the controlled rotation of the upper body. To achieve the locomotion and simple circular motion is translated through a pattern of flexible joints animating the rigid planes of the body. The modified water bomb spherical joint enables rotation and synchronized actuation of the front and rear legs. The material of the hinges and their design is critical as they allow the distribution of torque from the actuator through the whole system. While the pattern shows symmetry along the axis Y, the rotational motion creates asymmetrical and corresponding configurations. To take a step forward with the left leg, point 4 in the diagram moves away from point 3, while point 1 and 2 touch. As the torso turns going through a neutral position, the gait cycle repeats on the other side. When the right front leg moves forward, it lifts higher than the other 3. Once that leg touches the ground, the left leg, the hind leg lifts slightly. The method of fabrication allowed us to iterate rapidly and gave us several prototypes that show gait variations and navigation control. And for this, the type, number, position, and range of motorized rotation was studied in relation to the patterns of folds and connections. Tethered and untethered variations were produced, showcasing different levels of control. Chris 1, 4, and 5 were selected as origami robots that display key differences. In all the 20 centimeters and 45 centimeter Chris prototypes, the microcontroller and actuation components were housed onto the rigid ground plane. Here we see the step-in sequence of Chris 1 and Chris 4. An Arduino Uno with an Adafruit motor shield V2.3 was used to program the steered motor in the tethered creases, whereas lightweight Arduino Nano was used to program the 2 servos in the untethered configurations. This difference enabled variation in gait and steering. In Chris 1, the gait is slower and smoother than in Chris 4. Conversely, in Chris 4, the use of servos produces faster gait and the pairing of one servo motor to the one rear leg gives it the ability to be steered. A sensing capability was attained by implementing a Bluetooth control, and a pair of distance infrared sensors enabled the control of movements remotely and untethered. And you are seeing that in the video. And that's the untethered Chris controlled by a tooth, the Arduino code controlled the rotational angle domains for the motors. Both open and closed loop systems were studied. The first one allowed to steer Chris by modifying inputs through potentiometers. The prototypes that exhibited the best control in steering were Chris 4 and 5. To achieve this, each actuating beam was connected to their respective servo motor, and the repetition of movement of one hind leg in relation to the other caused the body of the origami to turn either right or left, and full rotation clockwise and anti-clockwise allowed the robot to backtrack its path. These two prototypes achieved sharp and accurate turns, unachievable in the prototypes using a single motor. Here we see a motor position to allow Chris to walk straight. Right turns were accomplished by increasing the frequency of the right servo motor in relation to the left. An Arduino was used to program rotational actuators, incorporating real-time feedback loop that permits Chris 5 to avoid obstacles while walking. The infrared sensors connected to the front legs measure the distance to any approaching obstacles, and a closed feedback loop was created between the IR sensors and the servos, where if an obstacle was far away, the robot will make a soft turn, and if the obstacle was near, it will make a hard turn. The gate is very challenging to simulate using traditional methods due to its multiple degrees of freedom and under-actuated mechanism. Therefore, so far, the work only validates and verifies one possibility of the kinematics of its motion. The transformation from flat to three-dimensional configuration was analyzed and simulating using Origamizer and Origami Simulator. The kinematics of the folded planes and the relationship between the actuating angles and the rear legs of the resultant motion of the front legs were studied using SolidWorks, Rhino, Grasshopper, and Kangaroo. As a fabrication method, a fast and inexpensive pop-up laminate construction was used, and this allowed us to create several iterations of laminated flexible joints, studying and optimized through using pop-up CAD. By establishing a relationship between the configuration of the folds and the resulting range of motion, this research, we think, efficiently achieves complex and compelling gait of an origami robot while minimizing the use of electromechanical actuation. Pop-up laminate construction combined with the principles of kinematics in origami folding offer a shift in design methods at scales ranging from the millimeter to the meter scale. And we think that this is a contribution not only to the field of robotics, but also to design, where the intended performance, efficiency, adjustability, and ease of fabrication are critical. For the last project, I wanted to share one of its inspirations first. While abroad in the rainforest of Ecuador, I was fortunate to spend with my students 5 weeks talking with members of the Selva Viva community, learning about their traditional building practices and building together a pavilion for the community that was hosting us. The observations by the indigenous people of orienting the waxy side of the leaf upwards to shed the water took me into another material research that I titled Anima Choreographed Matter. This work, I think, contributes to expanding the expressive potential of material-based responsive systems and animation. The word animation comes from the Latin animare, which means to give breath to, and a sign associated with living organisms is motion in response to external stimuli. As such, creating the illusion of movement in animation is essential to convey that something is alive. Activating lifeless objects is not only challenging for animators, but also for designers from many disciplines as the need for responsive and dynamic environments grows. Current animation techniques use computational tools, digital fabrication, and have recently integrated the use of real physical materials for their textural and formal qualities. However, most overlook the inherent possibilities in material to achieve a dynamic response demonstrated by responsive material systems. In design, there is a parallel between non-living responsive systems and the response inherent in living organisms, whereby a body perceives an external stimulus input, processes it in the brain, and sends information to the acting muscles, the output. It is not surprising that many responsive systems are inspired by interactions found in nature. I'm interested in translating this into an integrated design interaction in which geometry, material composition are linked to external stimuli to create a desired behavior. Examples of these responses are seen in self-assembled and programmable materials, 4D, 3D printing, self-folding, shape memory origami, to name a few. But these systems present smart interactions where material reacts to external stimuli. However, there is a potential to develop them further for their formal dynamic qualities as tools of expression, and by doing so, offer new opportunities for their actuation, quality of motion, and animation at different scales. So identifying the opportunities from this literature review, the following research goals were established. I wanted to design a material geometric system that responds dynamically, both predictably and quickly, a factor of seconds, to an external stimulus. Propose an economical and simple to fabricate material-based technique at a scale that is suitable for recording transformation and that is accessible to a wide range of designers interested in investigating material-based transformation. And produce an animation with such technique, and in doing so, explore the potential expressive and emotive content of the dynamic responsive systems. So as such, instead of creating the illusion of movement, I proposed an animation technique that uses the external forces to trigger a kinetic transformation in a material by harnessing the properties of the material itself and further increasing its capability. By introducing water as an agent of transformation to carefully design paper constructions, this research presents a method of animating material by producing precise and controllable movement. So first, the study of fundamental concepts of action and reaction and the analysis of relevant precedents were followed by identifying principles to design a responsive geomaterial vocabulary and the methodology to implement in the production of the material-based animation. This was correlated to behavior and aspects of choreography. We see here on the left that the linear origami designs some are simple and some are more complex, actuating in different direction and sequential stages. And on the right, we see designs that work across a plane and designs that deployed volumetrically underwater. To develop the vocabulary, digital workflows were employed to generate flat origami patterns that were physically tested by actuating them in water. For the animation, this was conceived as a sectional journey traveling from the surface of the water to its depth, passing through the line between air and water. This framework guided the development of the animated paper constructions. These three settings, surface, datum, and depth, established the circumstances for actuation and the context for the performance of narrative. Choreographic considerations within each setting, such as the articulation of movement, timing, and the use of space informed the patterns for the origami constructions. In the animation, the different perspectives related to each of these conditions were recorded, and the time to transform from initial stage and final stages was documented. So the type of movement was predicted and controlled by applying these principles and enhancing the anisotropic capacities of the paper. Here you see antagonistic actions in the paper constructions that were actuated by absorption of water at the hinges or folds and channeled to the top of the layer of the surface. These actions unfold the origami designs, whereas in the agonistic or contracting motions actuated by water absorption, the underside of the paper construction absorbs them while the top part has the wax. Additionally, the orientation of the paper grain is essential in controlling movement. The structural composition of the paper used was unidirectional, enabling it to expand, fold, and bend easily across its grain and less easily perpendicular to its grain, shown in these diagrams and their cross-sections. To determine the different flexing actions relative to fiber orientation, a paper test with radial designs was placed in water, and the water was absorbed. The difference in the way of bending and spiraling were observed and recorded depending on the orientation angles of the fiber. Also, wax patterns were selectively applied to tune the material's reaction to water absorption. Depositing wax on the top and not the bottom induces a curling action upwards. Applying it to both stabilizes the flat stage, and applying it to the underside produces downward curling into the water. Understanding properties of the medium, such as water surface tension, was key in knowing how to control the behavior of the origami pieces. Now I'll go in more detail, showing some of the designs for the surface, datum, and depth settings. Referring to the animated origami design for surface, the surface tension of the water provides an anchoring ground for the faces of the paper that are in contact with it. This allows the paper to start flat and then unfold or curl or both, moving without sinking. And these are the flat and actuated configurations. This paper construction actuates when in contact with water to produce these movements in a factor of seconds. And as water is absorbed, the differential swelling of the paper and opening of previously made folds occur, resulting in the predictable behaviors of bending, extending, and spiraling. The images above show a tessellation combining anchoring and agonistic actions. In other words, this design shows the activation of some areas while not others by applying wax on both sides for stable elements and applying wax only on the front to enable curling and relaxation. I'll show portions of the animation that I can share at the end of the talk, but I will share parts of it to highlight particular behaviors. A combination of different fiber orientations and wax applications were used to achieve more complex movements, such as the next one, this one, where the opening of folds and curling happens in tandem. Chain reaction behaviors were obtained by combining flexing and contracting designs. The orange elements actuate once the blue elements bend and open to deposit them onto the water. So you'll see this in detail and then later as a collection. As adhesion forces between the water molecules and the paper are greater than the cohesion forces between water molecules, a meniscus forms along the sides of the transforming agonistic origami, thus pulling the surface of the water. These enable pieces to come together like magnets. Temporal self-assembled configurations were achieved in the agonistic origami and controlled by the boundary of the flat patterns. In other words, as the designs bend into their three-dimensional configurations, they attract each other into self-assembled formations. In this one, I tapered the boundary to create pentagonal or approximating pentagonal, but also hexagonal in other ones that tessellated better, obviously. Then these temporal self-assembled configurations will dissipate as the design relaxes back into their flat stages. We will see that. Doing this research, I found that the water surface becomes a dynamic canvas for visualizing transformation. So in the animation, this effect was amplified by projecting images of regular lattices through the water surface. As the origami moves, it distorts the lattices, as you see on the slide. This self-assembly shows movement perpendicular to one another. And I liked very much how, as I lit it, the light that shone through the modified surface, a new visual imagery was projected onto the bottom of the tank due to caustic phenomena. So in this case, I was trying to work with that and to achieve a clover-like flower onto the projection. These are some images showing the graphic quality of the water distortion and caustics projections in relaxed and actuated stages. The temperature of water changes the surface tension, which translated into either slowing down the actuation or accelerating it. I was playing with that to control certain actions of the origami constructions. In the images above, we see an out-of-plane fold that then anchors a leg of the design to then try to latch back onto it as it curls. Didn't quite work, but it almost did. Here's a closer look at it, trying to tie a knot. And I'm going to leave that for surface, and now we'll go into that sectional journey to the datum, where the phenomena of total internal reflection provides mirror-like surfaces, creating animated visual symmetries. So here we see the antagonistic designs unfolding from before, but at the datum, they create these symmetries. In this case, the object was not curling inside of the water, but this was achieved later on with other designs. So a movement from flat to convex is obtained if the wax-treated side is facing downward and the side facing upwards absorbs the water. Therefore, by tapering the boundary of the flat pattern, this can puncture the surface of the water as they actuate, thereby enabling bending downwards towards the water. We can see these behaviors in a bit more complexity in the next video, and I meant it to emulate growth. So I designed flat paper constructions that when actuated, they transform into bees, flowers, and other creatures. In this case, the mirror-like surface enabled me to use the air as a backstage where I lit this design on fire, obscuring my hand in the internal reflection. They came together, and that was when the fire happened. Here we see a still on the concatenated motions, and a still of the extending, curling, and spiraling actions that you saw in the previous video. And now in the depth setting, the movements occur underwater. This enables the possibility of seeing transformations from both sides of the designs. By applying wax on the front and the back side of the paper in an alternating pattern and accounting for the direction of the grain, the flat origami displays rolling and sinuous configurations when in contact with water. Corrugations that reorient by trapping air bubbles give the designs a buoyant quality. In this next design features both extending and bending behaviors, and it starts as a flat strip that corrugates. Then it flips as a previously score hinge was made that happens upon activation, and then it corrugates into three-dimensional triangular form that attempts to close on itself. The one before worked a little better, but I don't have a video of that last one. I'm sorry, again. Anyway, So physical prototyping as well as digital workflows using Rhino, Grasshopper, and Organizer were developed to generate two-dimensional patterns and simulate the behavior of the animated designs. For the antagonistic actions, two-dimensional patterns were imported through Organizer simulate the unfolding. But for the agonistic ones, the final element analysis simulations were employed using Abacus, still very much in the process. To simulate the swelling of the paper, a heat expansion coefficient was assigned to the areas intended not to have the wax. An increase in temperature on those surfaces emulates the swelling of those areas. And this clip shows an increase of 20% to simulate the expansion ratio relative to the absorption rate. So the work aimed to propose a way of animating material that would be accessible for a wide range of designers interested in responsive systems. For this purpose, the proposed technique also was very easy. It involved the basically involved paper, a commercially available wax ink printer, and a tank of water to actuate the paper constructions. This made it quite easily to iterate and quite economical, and also easy to record the animations with a simple camera. In regards to the goals stated at the start of the research, a material-based system was designed and achieved dynamic transformations in response to external stimuli. Designed paper constructions actuate within contact with water to produce controllable behaviors in a factor of seconds. The type of movement was predicted and controlled by applying principles of folded geometry and by enhancing the anisotropic capacities of paper. To generate the specific behavior, the orientation of the paper was determined and wax patterns were selectively applied to tune the material's reaction to water absorption. The 15-minute animation produced was a proof of concept as a medium to investigate possible expressive characteristics of material-based responsive systems. Through the development of this animation, design limitations and possibilities were identified, which in turn placed demands on the development of the technique itself. Achieving synchronization, chain reaction, and self-assembly demonstrate targeted use of geometry and material treatment, as well as an understanding of the external stimuli to achieve nuances in the articulation of movement, where timing and the use of space were considered. The interactions designed here were more complex and intertwined than anticipated. For instance, the water became a ground for registering the motion of animated pleats, and this opened an array of different formal and dynamic expression. The research offers, in my mind, new possibilities for material-based responsive systems to be more expressive. The defined sectional journey of the animation include rich conditions for actuation and the exploration of narrative as choreographic aspects inform the design of the paper constructions, hopefully to awaken our imagination and to celebrate the alternative ways in which we respond to the ever-changing environment around us. Thank you.
Thank you, Olga, very much for such an inspirative talk. And I will ask you immediately, can we scale it up? It will be great if you can scale it, because now it's really on a small scale.
Yeah.
What do you think? Is it possible? Or will be possible?
Yeah, there were some designs that were bigger. It's just that some of these were so delicate that I like that feature about them. I'm not so sure that this particular one in its totality can be scaled up, but I think some of the ideas and sensibilities could be scaled up to create responsive systems that have the responsibility or have the demand of being more expressive. You know, we can say so many things with the way in which we move, and to me that's where I think this is a little bit of an introduction to then take one part of movement or one module of it and really think about a facade system that could could perform, not just as, let's say, the quantitative perspective or approach of performing, but more an expressive or theatrical way. Yeah.
Okay, thank you. Thank you very much. Do we have some further question?
Yes, Alexandros Ioannou from TU Wien.
Hi.
I have a little question actually. Your trigger is water, is it right?
Yes.
Yes.
The agent of did you say the agent of transformation is water.
Okay, I have actually a question because myself, I did something pretty close to what you do,
Oh, cool.
just with wooden lamels, and
Yep.
so as you said, the wood is isotropic as well, and my trigger was heat, so we tried to extract the water out of the heat for facade systems, basically.
Yeah.
And to be honest, I had some difficulties because in the one movement goes very quickly. So even with wood, I managed around 10 seconds for 90 degrees. But to bend it back, how long would you take for yours?
So for mine, I think the water, possibly its advantage was that I could put hot water and the elements will move a lot faster than when I put cold water.
If you take them out, so it's with the heat of the water that it changes then back to the original state?
So some designs are curled and would not relax back. Some designs were actually will come back. If I let them in water, they would open up again. But I have some, depending, I think, also of the thickness of the paper. When they curled, they stayed curled as three-dimensional configurations. So some of the one in depth or, many of them ended up just becoming three-dimensional configurations at the end and would not relax back.
No, okay, because I mentioned because I did a lot of experiments like this as well, and in the first phases I had exactly the same problem because initially we wanted to take them in facades, and I couldn't take them back, no chance. And now we managed to do this, but it's way slower than on the other side. That's why I wanted to ask if.
As you see in the video, some would actually go back right away, and some, I think, is because of the thickness of the paper. They rolled so tightly that they stayed in that configuration.
Thank you.
Thanks.
Yep, someone.
Thank you for the interesting talk, and
thanks.
I have plenty of questions concerning different projects.
Good.
Starting with the last one.
Yeah.
Is it one of the ones that you didn't use Origamizer? Like for bending?
Yeah. Yes.
Did you use or didn't?
Did not.
Okay.
Yes.
And what is the problem with, then you used or you're planning to use Abacus?
Yes, probably my capacity. But it was basically a heat coefficient given to a surface to emulate the swelling of. Because as it absorbs, then the underside was creating a curvature that the other was a differential curvature, right? So it was different, the top curvature than the bottom curvature.
Yes,
one was
all in all, it's like a cylindrical shape, right? The bending is to, if not cylindrical, a conic surface. It must have rulings so you can easily simulate it.
I would love to collaborate to talk about that.
Yeah, we can talk about it later on.
Yes.
The other question.
I think I was just worried about because it inflates basically, and it swells.
Okay, so maybe I misunderstood or missed something. Then regarding the robot, the origami robot.
Yeah.
How was your workflow starting with the count of the number of degrees of freedom, or you, like, because you mentioned you synchronize the movement of the legs, and that decreases the number of degrees of freedom. And you, like, yes.
I don't.
Do you keep it in a certain number to control the movement as exact as possible, or?
I think it was a little bit. It was trying to validate what has been done, what was done materially, more than necessarily keeping the degrees of freedom equal to the number of legs. So the main idea was to minimize the actuation by connecting all of the folds together, having a ground pretty much with a rotational motion. So the degrees of freedom ended up being many in that at each joint, even though they were synchronized, they
Because may I add this, you start with a developed surface,
right,
and a certain pattern with straight crease lines,
yes,
which should act like rotational hinges and rigid,
but flexible joints. So
and this should have a certain degrees of freedom that you can count.
Yeah, it wasn't as straightforward to me when I was looking at that. Yeah, and in consultations with C's at Harvard, it seemed to be quite difficult as well to look at the degrees of freedom because of the synchronicity of all of those hinges, basically.
I see.
Yeah.
Thank you.
Thanks.
Yeah. Thank you very much, but that's really the new topic for you to further to study. That means that now we open one box with the lots of the idea. Thank you very much,
Thank
Olga,
you
again. And cut.